consider what happens when we have a reaction that starts at equilibrium and we manage to change the pressure. Now, I'll note that there are several ways that one can change the pressure in a reaction mixture. So let me denote some of those ways, several ways to change pressure. Okay, the first and maybe most innocuous way to do this is to simply add an inert gas to our reaction mixture. And by inert gas, that could be a noble gas, or it could just be some substance that does not interact or react with any of the reaction species. So you add inert gas to increase P. And as chemists, I hope you can anticipate that the net result of doing this is no effect. In fact, this has absolutely no change on the equilibrium position or status of the reaction that's in that vessel and at equilibrium already. Now, a second thing we could do would be to change partial pressures. So we could add one of the reaction species, or we could change several of the reaction species partial pressures. So I'll just denote that as P sub alpha. But this is really no different than the thing we talked about a couple of videos ago. It's just a composition change, and that's a fairly straightforward effect when we're talking about taking a reaction at equilibrium and changing its conditions. The third one is the one I want to focus on, and that's one where we might change the volume. All right, now that you might say, well, what are we doing? We're changing the pressure. Well, I'll remind you that for an ideal gas, we have the condition that pressure is basically equal to RT over volume. And generally, it's true whether it's an ideal gas or not, that pressure and volume are inversely related to one another. So that means that as V increases, I'll have pressure decreasing. And as V decreases, I'll have pressure increasing. All right, so there's an inverse relationship there. And that's what I want to track now by changing the volume here. All right, so how can we deal with this in a systematic way that will allow us to see what the change is going to be in delta G from doing this? Well, first, let's take our just a generic partial pressure for one of the constituents in the reaction mixture. And I'm going to say the new partial pressure is going to be given by some number, lambda, times the original partial pressure. So the partial pressure that represents an equilibrium mixture, I'm going to scale it. So lambda is just basically a scaling factor. And if you had an ideal gas, that scaling factor, might be this. Okay, we're going to scale it by the different volume that we're scaling scaling the whole reaction mixture by. Okay, but whatever it is, lambda is going to tell us something about how this thing changes. Now I'll note a couple of things. One, if I'm decreasing the pressure, that means that lambda in this case is going to be less than 1. In other words, it's a fraction, so I'm decreasing the pressure. If I'm increasing the pressure, then lambda has to be greater than 1. Okay, so there are going to be at least two different conditions here that are going to affect the outcome of doing this. Now, what I want to do is go back to an equation that we've written down a couple of times, and that is to say that the Gibbs energy change is equal to RT log of the ratio of Q to K. Okay, now what we're going to be focused on here is Q. And I'm going to write Q as though our hypothetical reaction is one that takes place all in the gas phase, so everything is a gas. So that would simply be written as the pressure, the partial pressure of component C raised to its stoichiometric power. Same thing for D, and then divided by these quantities for the two reactants A and B. All right, so what happens, this is now, if at our initial condition, this is equal to the equilibrium constant for the reaction. Okay, so we'll call this the old condition. And Kp will still be the value that we have down here. All right, what happens in the new condition? So what would Q new be? All right, well now I'm going to scale all of the pressures by the same amount, because when I change the volume, I'm not just changing one partial pressure, I'm changing them all, and I'm scaling them really by the same factor. Okay, so in this case now my reaction quotient is going to look something like this. Okay, where again I have the products divided by the reactants. And I know when you see this, it's tempting to say, oh, okay, so all of those lambdas are going to cancel now. But the lambdas are raised to different powers. And this is where the fun comes in. Because this Q nu is basically going to be just equal to this scaling parameter lambda times the change in those stoichiometric parameters. And remember, since the original Q was equal to the equilibrium constant, then this is just going to be equal to lambda raised to this power times the equilibrium constant. Now I'll specify that this delta V is going to be Vc plus Vd minus Va minus Vb. Oops, Vb. All right, so it is the change in these things. And if the number of gaseous moles in the products is greater than the number of gaseous moles in the reactants, then delta V will be greater than 0. And if the number of gaseous moles in the reactants is larger, then delta V will be negative. Okay, so now when I take Q nu divided by Kp, in other words, when I want to construct this ratio here, what I'm going to have instead is the following. I'm going to be able to write down that delta G is equal to RT times log of, now this is this divided by Kp, so it's just going to be lambda raised to the delta V. And I can rearrange this a little bit to write this as delta V times RT log of lambda. All right, so I think you can see where we're going to have to do a little bit of work. We're going to have to consider the possibilities of lambda being either less than 1 or greater than 1. We're going to have to consider delta V being either less than 1 or greater than 1 as defined by this. So let's take a look at those possibilities. I've got them written down actually on another page. So let's make a chart, and in this chart what we're going to do is look at the different possibilities for lambda and for delta V. Okay, so for lambda, if I increase the volume, so this, I'm going to look at this section here first. If I increase the volume, that means I'm decreasing the pressure, which means that lambda is less than 1, which means that log of lambda is less than 0. Okay, now my delta G is going to take on the sign of the product of this sign times this sign. Okay, well, if log of lambda is less than 0 and delta V is greater than 0, that means overall my delta G is going to be less than 0. All right. Similarly, down here, if delta V is less than 0 and log of lambda is less than 0, then the two of them are going to form a positive product and delta G will be greater than 0. So I'll have these two results. Okay, similarly, if I decrease the volume and increase the pressure, that means log V is greater than 0. And if I combine that with a delta V that's greater than 0, then this will also be greater than 0. And finally, the last combination is if log of V is greater than log of lambda is greater than 0 and delta V is less than 0, then this must lead to a negative combination. All right, so we need these 4 outcomes for delta G. Now I'll remind you that when delta G is less than 0, what that means is the reaction is going to proceed spontaneously in the direction that it's written. That, in other words, it's going to shift toward the products. And when delta G is greater than 0, it's going to shift toward the reactants. What we see in general, and you can track this with these different changes that I've indicated on this chart, is that when we increase the pressure, that is, we decrease the volume and increase the pressure, the reaction will shift to the side of the equation that has fewer moles in the gas phase. If we increase the volume and decrease the pressure, then the reaction will shift to the side of the reaction that has more moles in the gas phase. Now, I should mention that sometimes delta V equals 0. And when delta V equals 0, Up here, that means delta G is equal to 0. And what does that mean? It means the reaction is going to stay at equilibrium. It's not going to shift in either direction because the change in volume has not measurably changed the equilibrium condition.